Okay, let's officially start this. So I'm sharing my screen. Hi there. I'm Noah. I'm a lead smart contract auditor at Hacken, working on Solidity and now even Rust audits. Sort of insider info, but there's even going to be some Lisp stuff for those familiar with that hack. So fun stuff. And today I'll be telling you a bit about something that's actually, since I first started talking about this topic, really evolved, but the presentation doesn't reflect it fully yet, and which was initially just a 2-week research project and is now a funded research that's going on at Hacken. Honeypots, hacker traps on the blockchain. So since this is not a crypto conference, let's start with a little intro to the blockchain. An Ethereum crash course. So Ethereum is a blockchain, just like, for example, Bitcoin. But the main difference would be that on Ethereum, Ethereum is Turing complete. So while on Bitcoin, you can only send the Bitcoins back and forth, on Ethereum, you can run more stuff. You can run some advanced code, which is what makes it really popular these days. The second biggest coin, right? And to allow for that, Ethereum has an additional structure. So along with externally owned accounts, which are like normal user accounts, which have an address and a balance, and they're called externally owned because they're owned by a private key. Like there's a direct connection between the private key, public key, and the address, and no one except you has access to that private key. So along with those, which are also on Bitcoin, there's contracts which have an address, but that's not controlled by a private key. They have a balance, but they also have code, which is pretty much storage for the bytecode that runs that is the contract, and storage for the state of the code. On Ethereum, all interactions are done through transactions. So an end user account can send a transaction containing data and some value to a contract, and the contract can then do nothing or send transactions to other user accounts or other contracts containing, again, data and value. This allows for pretty fancy systems. As I said, Turing complete. So to develop some smart contracts, you need to pick a language. There's a few choices, actually, ranging from assembly, like just raw bytecode. But the most popular option right now is Solidity. It looks something like this. It's pretty similar to C. It's an easy language. Along with the normal feature set you'd expect from any EVM, it has some blockchain specific codes, but it's pretty easy. And you run this code through the Solidity compiler, get this bytecode, and using a transaction, put it onto the blockchain, and it becomes a smart contract. So now it's on the blockchain. It runs on the Ethereum virtual machine. It is Turing complete, registerless, has a gazillion of opcodes, and some of the important features are that execution costs gas. Gas is a mix of time complexity and space complexity, and it's a way to prevent spam on the blockchain, and also that deployed code is immutable. Though there are ways around it, in general, if you put a contract up, it's there. So instead of your intern mistake being a database corruption or breaking production, your interlevel mistake costs about $1,000 in gas to fix because you just uploaded the wrong code or had a little bug in the contract and you cannot really fix it. But there are ways around it with proxies and upgradable contracts. The state of the contracts is mutable over multiple transactions. And that's also useful because, you don't have to do everything at once in this gas limit. You can do it over a longer time span. Now I'm just going to do a quick check if everything is working, if there are any comments saying stuff is broken. No? Okay. Okay, so now that we understand how smart contracts work, we're going to get into exploiting them. So since the beginning of time, there has been a gazillion hacks. It started with the DAO hack, which led to an actual fork of the blockchain, continued through the DeFi, continued to the ICO period with a ton of terrible hacks. And these days, it's mostly DeFi, GameFi bullshit, and generally off-chain projects getting hacked. Since the beginning of this presentation, time averaged, $400,000 have been stolen. It's a pretty big problem. So you must want to be a hacker right now, right? Well, it's not so easy. Say as a hacker, you find a vulnerable target, right? And you try to send a transaction, right, to attack this target. You send your transaction, but somebody overtakes you. This is called a front-running bot. They work by reading the mempool, which is where all the transactions sit until they're done, and sending a transaction that has more value, a higher gas price, and overtaking you. But it's not our topic, but it's really important to know in general. What we're talking about is an alternative. You think you found a vulnerable target, but really it's a honeypot. It's a fake exploitable contract. That gets us to our topic for today. So honeypots. What are they? They're smart contracts that look vulnerable, but really aren't. The big idea would be to make hackers believe that they can exploit the smart contract by sending funds, while really only the creator can retrieve them. In general, you want to fool a person like me, or a person like me, but my anonymous identity that really does all the big hacks that you haven't heard about. And get me to send some money because I think I can get some money out of it, right? You need to spend money to earn money. You sometimes need to spend some gas money or general funds to change the state to hack a contract. It's about fooling me into doing that when I really cannot gain anything. So to get into an example, there's going to be a tiny bit of code, but it's really simple, like total 10 lines. On a smart contract, for example, we have, this is like the school level example. We have a function, multiplicate. This is a honeypot. This is a tiny element of this honeypot. And it's a function, multiplicate, payable external. What that means is name of the function, right? Payable means it can receive the value of the transaction. That would be the message.value here. And external just means that pretty much anyone can call it. And then in here, going slowly, we have the if. So if message value, if we send more than this.balance than already is on the contract, then address.message sender, that's us, a dot transfer will get this.balance plus message value, which is everything, all the monies. And you may think, okay, wait. So if there's like, I don't know, $100 on the contract, right? And I send 101, that means I'm gonna pretty much instantly get my money back and like 100% gain, because it's gonna send me $201 and I spent 101, so $100 profit, yeah. But not really. See, this is made to fool you. Because this balance already includes however much you sent. That means that when you send the $101, this balance is not going to be 100, it's going to be 201. It's going to be 201. That means that message.value is not bigger than this.balance, and this is just an unexecuted if block, and this function simply happily takes all of your money. That's all it does. So an impossible conditional branch in fancy words. So this is a cool example, so no real, application. Let me just check if there's any questions for this one. Nope. But moving on, like this is a real world example. It may seem daunting right now, but let's again focus on just one function. So let's look at this function stake on the right. So function stake is payable external. We already know what that means. It takes some money. And we're going to have an if message.value. So if we send more than largest stake, okay, largest stake, it's not a special thing. It's just this variable above. And what happens if we send more than the largest stake? Well, we become the owner of the contract, right? Owner equals message.sender, and message.sender is us. And largest stake becomes the message.value. So however much we sent. This is actually honest code. This actually happens. So if we send more, it's gonna make us the owner, and ours, however much we sent, is gonna become the largest stake. That's not the honeypot. The honeypot in this case is somewhere else. See, we become the owner here, right? And below we have the function withdraw, which is an external only owner. Only owner would mean only the owner can call it. And that does the magic, right, that we want. The address message sender dot transfer this dot balance, give us all the money. And we may think that we become the owner, we can call this only owner. Because there's this like ownable contract that's being inherited and all the magic tech words. And it has this modifier that checks. So on the left, modifier only owner, in the contract ownable, it requires that message sender is the owner. But for those getting ahead here, you may have noticed there's two owners. So top line of the first contract and of the second contract, you see address public owner. It's being defined twice. So when you become the owner in the stake function, you become the owner on the right contract. But the owner that can call the only owner function is actually the owner in the left contract. And that one is never changed after it's defined through the constructor. This is something called variable shadowing, and it's another common technique. This one actually has practical cases, and it's quite successful. So looking at an example, I'm just going to drop this Linktree link here for anyone that wants to follow along on Etherscan. So it's in chat, guys, if you want to follow along on Etherscan. But I also have the screenshots, so we didn't have to hurry. If you do want to follow along, though, it's the KOTH example, King of the Hill example. There's a few others, a few other useful links, so keep it in mind. So for this example, we can see, a contract, the description, the comments say simple gain. Each time you send more than the correct jackpot, you become the owner of the contract. As an owner, you get all the money. At least that's what they like to believe. But that's not how it works, as we saw. So we can see people are doing the transfers. They're trying to become the owner of the contract. They send 0.1 Ether, then 0.11, then 0.21, 0.42, etc. More and more money, until we see that the real owner runs the take all function and takes all the money out. And the real owner has amassed on just this one account, and I'm sure they have like 200 alts, like 3 point something Ether at the current price. So like $4,000 would have been $12,000. It's not much, but this is like one guy, one account, actually, not even one guy. We don't know how many accounts this guy has. And yeah, fun stuff. So this is how they look when they're successful. Very, very profitable. This took no work, and this guy earned that money in like a few days. So nothing really. There's only one more code example don't get scared. This is the final one. And this one, I'm not going to get too deep into the code. I'm just going to give you the logic, because this one is the one that makes me the saddest, but it's also the most successful one. It makes me sad because this is an easy to fix issue that could have fixed by Etherscan, which is the transaction viewer for blockchain stuff. And it's really just an UI issue, nothing more. And it's the most successful, mostly for the same reason. Because people tend to trust Etherscan. So this is a gift box. How it works is, if you know the password, or if you can guess the password, you get the gift. The password setting is done in a secure way. You can see in the get gift function using the SHA hash, which is a good way to do the passwords. And we can see the address message transfer. So all the stuff we're familiar with. Get gift, the second function on the left, just gives you the money if you can guess the password. The way this honeypot works is it fools you into thinking that this was incorrectly set up and that you can maybe exploit it by setting the password yourself and getting some money out of it. So I don't know, you see this contract and there's like 2 Ethereum on it, and you look at the code and it says set pass, and it shows you that if the password has not been set, we're looking at the set pass function. So if the password has not been set and you send more than 1 Ethereum, you can set the password to whatever, and then afterwards you can get the gift. You can claim all the monies. And it looks like that. So I'll just skip this completely unimportant set hidden function on the right here. It's totally unimportant. Just ignore it, right? And I'm gonna go straight to the example because, as you can see here, people tried to set the password and they tried to get the gift, and they didn't get the gift. Something went wrong. And what went wrong was that they couldn't. This is sort of a detail. So, but they couldn't see all the transactions that happened. They saw only a few of them because of the UI issue with Etherscan. And the really important ones, the ones that make the honeypot, are here. And as you can see, this looks like gibberish. You cannot tell what happened here. But if you look into it a bit deeper, you notice that it was another contract. So instead of an end user account, a contract calling this set hidden account. And that relies on abusing Etherscan because it does not display the zero-valued internal transactions. And that allows the owner to trap some of the deposited Ether in the contract. And what happened here, so this set hidden, it just said the pass has been set to true. And that means this if block becomes, again, just a function that will happily take your money. And in this example, you can see I actually had to switch the switch here to see more of the transactions, and I still do not really have the data, so I need to really look into them. So yeah, it's a tricky one. Anyway, that was all for the code examples. Let me check if there's any questions. Nope. So back to the slideshow. So those are like 3 major examples of honeypots. I hope this wasn't too hard in terms of tech and like code, but this is the general logic of them. They're about fooling us, the security experts, aka hackers, into believing we can exploit something. And it's usually about tricky semantics, but there are some really fun examples. You'll see later when I go into the results. So hackers actually search for exploits in newly deployed code. That means because they're racing to get some money out of the exploit, they don't really have time to check. This is not about catching me, the guy that has 6 months to research this. This is about catching the guy who just saw this exploit and he needs to do it now. He does not have the time to check if it's really good, because it's a perfect opportunity to score like $2,000 right now. Okay. The second thing is when you're not really exploiting hackers, but rather exploiting tools. So for example, there's this tool called Theo, which automatically exploits stuff. And you can probably write a contract that's gonna exploit an issue with Theo and thus steal money from TO users. And the third thing is the complexity of the Ethereum ecosystem. And that's just a gentle reference to Etherscan sometimes sucks, aka the gift box example, which makes me sad. So now that we have an idea how they work, we can go into detection. We can look at how we can actually find the honeypots and figure out how they work. There's two methods for this. Method one, symbolic solving. So I have a background in formal logics, at least a bit of a background. And in general, the way this works is you turn the code into like a logical problem, into a logical equation that you can solve. You turn all the important bits in the code into symbols, and then you can replace them with anything, and you can write like a thing that detects stuff that way. For anyone that's used like scientific Python, like SymPy, like the symbolic programming libraries and stuff like that, it's pretty similar to that actually, but for general execution. And there's actually a tool for this, a previous research done about 4 years ago called Honeybadger. There's a link in the link tree to their research paper. The other option is going with ML classification, so machine learning, just throw whatever and hope it sticks. In that case, we need some data set for which this prior research on symbolic solving is very useful. And we can then find some transaction patterns, do some unsupervised learning, and see what comes out of it. One nice thing about it is because of the general, pattern finding of unsupervised learning, we can find novel honeypots by classifying, whatever, instead of requiring only the specific solutions, because symbolic solving requires you to write a detector for each exact type of honeypot with very little variation, while the ML stuff can just find, the general transaction patterns and figure out, yeah, this is probably a honeypot. With that in mind, this is like the general process I went for originally, trying to replicate the work of two previous researchers about 4 years ago, because I'm reviving this sort of dead topic, right? And the first is get all the valid smart contracts. So, you crawl the blockchain, you get everything that's on it, you make sure it can deal with cash, because you cannot earn anything if you're not scamming people for money, and you get like a nice base of contracts to work with. Then we use Etherscan, because on Etherscan, people will often verify the code. So looking like this, you can see contract source verified, and we can check the code that's been verified, and it can be a useful thing in analysis. Then we run the symbolic analyzer Honeybadger, and we get a list of 50 addresses or something that are honeypots, maybe even more, and we store and label these for ML training. We could get a lot more though, looking at clones that perform differently. So it's a useful thing. And then finally, we classify it using ML algorithms, which you can read more about in the second research paper linked, the ML method. But it's pretty much just unsupervised learning, and let's see what sticks at this point. And then you run the train models on new data and try to find something new. The results of this are sort of funky. So this analysis took about scanning of 2 million contracts, because my time was very limited initially, of which only 150,000 were unique. There were a lot of copy-paste contracts. Of those unique ones, 50,000 dealt with cash flow. And from those unique ones, we found 300 honeypots. And when checking through some of the data, it turned out some of them were actually false positives, and we get like an okay accuracy and like false positive rate there. By the way, this 300, it's actually like 2,500 deployed ones because we're looking only at the unique ones at this point. The types detected, this.balance, the balance disorder, there were actually a few of those. Then we had the hidden state update, the most popular one, which was the give box, right? And we had the inheritance stuff, which is like the variable shadowing from the second example. So those are the two most popular types they actually showed you. You can find more of the taxonomy in the Honey Badger paper, actually, because I'm still using their taxonomy while making my own. Thanks to this research, we actually found two new ones. I love the first one. I really love the first one. So if you ever heard the joke, if you really want to mess with a coder, go into their code and replace all of their like the Greek question mark or whatever, the character. Replace all their semicolons with the Greek question mark because they look the same. And they're gonna go crazy. Well, sometimes in the smart contracts we actually process strings for like stuff like roles have names, and what these guys did was they made two roles, okay, that looked pretty similar, but they use different Unicode characters. So when you read it, it looks the same, but it's really not. So you would try to run like an only owner function, which had like a role of one owner, but like there was a mix. There were actually two different owners with mixed permissions, and it's really just crazy to read the code. It's a bit better in a dedicated IDE, but just like looking at it on Etherscan, glorious. So that's a really creative one, and the second one is just about fooling the reader. So an unexecuted call. If you ever used a programming language, you know that always a function call is gonna be ended with like some parentheses. It's pretty similar in Solidity. There's a special operation called a call, and what they did was they just wrote the call, but they didn't close it all at the end, and then they add all the data, so it's never executed, but it's in the code because it compiles down to nothing, right? Because it's just a reference. So it fools the reader. And this one, actually, both of these are this one is undetectable by symbolic frameworks because there's nothing in the code to detect. It solves the bytecode, the framework. While the role encoding trick, yeah, it's detectable, but this is way more fun. It would probably be more detectable with something like just a check for fancy Unicode characters. So those are the novel ones. Some insights from this are that these guys are actually fairly successful. Based on the ones we found, I'd say these guys have a lot more money now because this is all sort of old data still. We need the new data, and that's going to take some work, some more research. So 70% only trapped one victim because when you see on Etherscan that it was exploited, you won't fall for the same trap. Most are exploited quickly because hackers check new contracts, and the hidden state update exploits are the best because UI UX issues are a big problem on blockchain. Monthly, they get really popular as the Ethereum price goes up. I only have data for 2018, really. So I could tell you more when we get to 2020 and 22, 21. Would be really interesting to see what happened to the types and the deployments. But yeah, they tend to do well when the price is high. Because people don't think as much. They're like just trying to get something, a lot of that FUD stuff. They're very profitable. So just in this like 1 year period, the ones we found collected 250 Ethereum. The best performing one stole 12 Ethereum, just a single contract. But I'm sure there's like a gazillion more we haven't found. And I'd guess that in that 1 year, probably like 1 million or 2 million were stolen using honeypots. And in total, the total would be like 20 million by now, or more, but that's something I'm hoping to find out. On average, the median was 1.76 Ethereum, and most of the profit was made through hidden state updates, the gift box style ones. Detectability, we found 269 unique ones, but the accuracy of 91% is really for the false positive, false negative stuff. We want to find more of them, and we can drive down the accuracy to get like a wider set. But that's something that I'm playing around in the research. And right now there's no public database, and I'm working on that opportunity. So yeah, that's pretty much it about Honeypots for me. We can move to a Q&A session. Yeah, I know. The Greek question mark is a wild one, and the fact that somebody used it to exploit people like this is like level 2 evil, because it's usually just a joke people say and not something that people use to steal thousands of dollars. Yeah. Moderation panel. Okay. Mateusz Borowski, welcome. I think I just added you. I really hope I just added you. I clicked the plus button. So, any questions? Any clarifications needed for the code? Any questions about the research data? You can write them in the chat on the right. I'll give you guys another 2 minutes if there's no questions. I guess everything was clear, right? So I'm just gonna repeat the link, so you can go here to the link tree if you'd like to see some of the research papers, the link to the presentation, or my LinkedIn to follow my progress. And yeah, that's pretty much it. Thanks all for having me. It was great talking about this topic again, and see you next time. Maybe next week in Belgrade, actually. There's going to be a conference, but I'm still waiting for the confirmation. Bye-bye.